The last thing we're going to talk about this week is the model output for STAN models, how we can compute Bayes factors and what they mean. And we'll talk a little bit about effect size for Bayesian models. So to access the output of the rstanarm model, we can call summary, as we saw before. But of course, there's a hitch. In Bayesian analysis, there really isn't as clear a distinction between fixed and random effects. By default, the summary output will include every cluster-specific parameter. That includes every cluster intercept and every cluster slope. So if you have 100 clusters, you're definitely going to get, and you include random intercepts, you're definitely going to get 100 intercepts. And if you include random slopes, you're going to get 100 slopes for every parameter that had random slopes. That makes the default output extremely cluttered when you have a lot of clusters. Why would they do this? The reason is that in the frequentist tradition, these cluster-specific effects aren't necessarily interesting. They can be, but we don't really test them with p-values. We don't use test statistics on them. We do that with the fixed effects or the population effects. That's the term you'll see more commonly in Bayesian analysis. This is partly a practical issue. It's just not feasible to go through every cluster parameter and test and report it, or compare each individual parameter to a single null. And it's also just not that interesting necessarily to say, is this, is each cluster parameter significantly different from zero? You typically don't even have directional hypothesis about, the individual cluster parameters. It's going to be the same hypothesis for every cluster parameter. So why do we care about going through each one? In Bayesian tradition, this distinction isn't really as sensible. All we really care about is estimating our uncertainty, and there's no reason we shouldn't do that with the cluster-specific parameters. This is, in a sense, one of the reasons hierarchical models are so well suited to Bayesian analysis. We can think about each cluster-specific parameter as being a realization of the probability distribution of the population parameter, or the fixed effect. So we can say that cluster number 1 is part of the distribution of the fixed effect. Cluster number 2 is part of the distribution of the fixed effect. So they're all, each cluster intercept is part of the distribution of the population intercept. And then we could also see each cluster as having its own dependent probability distribution for its parameters as well. Whether we care about these cluster parameters or not isn't a practical issue in Bayesian analysis. There's no reason we shouldn't estimate these things. It's 100% about the research question and model performance. To get a clean output that mirrors what we've learned so far, we have to ask for the particular parameters that we want with the pars and regex pars arguments. In the pars arguments, we can always get our gammas and our sigma epsilon. Note this is standard deviation, not variance. So the fixed population intercept is always alpha, and this is true for other models too. So any fixed intercept in a normal regression model, beta 0, we call it alpha here. There's just different parameterizations for these types of things. The fixed population slopes, the fixed or population slopes are always beta, and the level 1 residual is always sigma with a little s. So those are easy to get. So if you just ask for alpha, beta, sigma, it'll give you it'll give you the intercept, all of the slopes, the fixed slopes, and the level 1 residual. We can use the regex pars argument to search through any other parameters, to access the ones we want. So if we want all of our level 2 variance parameters, our random effect variances, we could use regex pars with capital S sigma, and that'll give us our variances and covariances. And I don't know why, but it treats these differently from the level 1 residual. The level 1 residual is in standard deviations. The level 2 are in variance and covariance. Credible intervals are another thing that comes as part of the default output. These are the corollary of confidence intervals in frequentist analysis. And credible intervals are more straightforward than confidence intervals. Estimating this type of uncertainty is the bread and butter of Bayesian analysis, whereas it's a little bit more convoluted in frequentist analysis. Confidence intervals in the frequentist tradition represent the estimated range of values for the mean of the sampling distribution. This is kind of interesting. It gives us some information that we can make use of, but it's a lot harder to intuitively interpret. Credible intervals are literally the probability range that you think the parameter could fall within based on your model. It's saying that there's a 95% credible interval. You're literally saying there's a 95% chance that the parameter is inside of this interval. It's very straightforward. We could specify any quantiles we want for the credible intervals with the probs argument. So if we do 0.25, 0.5, 0.975, that'll give us the 95% credible interval as well as the median. And you can always put a few in between, doesn't hurt. So here I load up my data, fit a model, and this is the same model we looked at in the previous slides. And then I call the summary. I ask for alpha, beta, sigma in pars. I ask for capital S sigma and regex pars to get my my hierarchical variances, my level 2 variances and covariances. In this case, just variances because of how many random slopes. And then I get my credible intervals with probs, and I just specify digits equal 2 just to make it easier to read. It just rounds everything to 2 digits. So the output's too big to naturally print on these slides when I knit. So here's a screenshot of what the output looks like. And so you see at the top, you get your model info, which is very similar to what you'd see in any other output. It gives you all this other, all the info about how you fit your model. And then it gives you your actual output. At the bottom, you see the top of the diagnostics part of the output that we looked at last time. So the first column is the mean. The second column is the standard deviation. Now this is the standard deviation of the probability distribution for each parameter. This is sort of like a standard error. But then we also have the credible intervals. So the interpretations for these fixed effects, they tell us what range of values the parameter might be in, and we would probably use the mean and or median as our best estimate. It depends on, it depends on what you're interested in. A lot of times the mean will be your best choice. That will minimize squared error. This goes back to what we talked about when we did that digression on variance earlier in the semester. But here we see for gamma 0, 0, the mean and median are the same. They're often going to be for fixed effects because those will often be symmetrical distributions. So the mean and median are both 3.77. The credible interval is 2.51 to 5.01. So our best estimate for the intercept is 3.77. And our belief is that there's a 95% chance that it's between 2.51 and 5.01 based on our model. We could interpret the coefficient for pain the same way, gamma 1, 0. So the mean is negative 0.06. The median also negative 0.06. And there's a 95% chance it's between negative 0.10 and negative 0.02. So in this case, the credible interval is really tight. So we're really confident that this parameter is, something in the low negative 0.0 something range. So this is this is a very narrow confidence credible interval. And so we have a lot of, our model really gave us a lot of evidence about this parameter. And we'll see that a little bit more as we go. And we could proceed on with each other parameter the same way, interpreting it the same way. So here we see gamma 0.2, which is the one coefficient for MSTAT. On the other hand, our best estimates are that it's 0.02 or negative 0.01, but the credible interval is much wider here. So even though our best estimate is negative 0.02, we really don't have a lot of belief about this parameter. It still could be kind of in almost any range, not any range, but it's a much wider range than it was for pain. But we don't have any evidence that it's positive or negative or what. And so if we're really going to make any sort of assumption about what this parameter was, it would probably be pretty close to 0. But keeping in mind that we really don't have strong evidence for what it is one way or the other, it still could be in a pretty wide range. And then unlike in frequency analysis, we actually just interpret the variance parameters exactly the same way. So the level 1 residual, again, we have the mean and the median. This time they happen to match. Sometimes they'll be less likely to match for variances because they're not symmetrical. They have to be positive. So the 95% confidence interval. So again, we just interpret this the same way. We're very confident that the level 1 variance is between, is in this 1.2 range to 1.3 range. And then the same for sigma mu 0j, our random intercepts. We could also get the highest density confidence interval. This is definitely going to be more appropriate for variances. Here I only printed out the fixed effects, I can't figure out how to get at this for the level 1 residual. You can get it for the level 2 residual, but here by default it just prints out the fixed effects, which for symmetrical distributions it's almost never going to be different from the equal-tailed credible interval, but it will for non-symmetrical distributions like variances. So the way they seem to have set this up is not exceptionally useful for us because it's harder to get the variances, but either way, there it is. So now we'll talk a little bit about Bayes factors, and Bayes factors are probably the most popular method for doing some kind of hypothesis testing or something like hypothesis testing and model comparison in Bayesian analysis, but they're not without controversy. And the instructor who taught me Bayesian analysis at Columbia really was not a big fan of Bayes factors. He gave us some other tools for doing model assessment, but Bayes factors are more popular, definitely more popular in psychology, and they're what you learned a little bit more about in lecture. And I do think that they have their uses, so we'll talk about them here. But there are several concerns with them, one of which is that people I think are a little worried that we're just going to wind up setting arbitrary cutoffs, which I don't think is a super founded concern, but there are some other concerns that are a little bit more founded. They don't want them to become like p-values, essentially. So what are Bayes factors? Bayes factors compare the likelihood of the data given the new posterior distribution. So they can compare different models, or they can compare two hypotheses. So they're kind of like flipping things back and forth. When we estimated our model, what we were getting was p theta given theta. Now we're going back to p theta given theta, but the theta is our new theta. This is our posterior theta. In maximum likelihood, theta is treated as an unknown. Now we're treating theta as a known quantity, or p theta as a known quantity, which is based on our posterior p theta given data. So in a sense, Bayes factors are a Bayesian way of assessing model fit, or how well the model reproduces the observed data. Because we're going back to say, this is what the probability that we would have gotten this data from this model. So in practice, the best way to get Bayes factors from stand models is with the bridge sampling and Bayes test R packages, and these two build on each other. And so to use these models, you actually have to specify an extra argument when you fit the model in rstanarm, a diagnostic file. And so on the next slide, I'll show you to do this. I'm fitting 3 different models, one with random slopes for pain. I've been focusing on random intercepts in part just because it's a little slow to keep fitting the random slopes model. Then with one with no random slopes for pain, this is the same model we've been looking at. And then one with only MStat, but not pain or active. And this is so we can test pain and active above and beyond MStat. So here are the 3 models. And note that here I am creating these diagnostic files. You also might note that I changed the DAP delta here, and I increased the iterations here, increased the iterations here too. This was to get the models to converge. So once we fit our models, we can create bridge objects out of them with the bridge sampler function from the bridge sampling package. And then we can call the BF or Bayes factor function on bridge objects to get our Bayes factors. One of the great things about Bayes factors is you don't care if the models are nested. In this case, these models are all nested, but it doesn't matter. You can, as long as the models are fit on the same data, then you can go ahead and go crazy with Bayes factors. So here we get Bayes factors on bridge objects. So here I'm comparing the fixed slopes model to the model that had random slopes, and this output tells us the data was 152.26 times as likely to be produced by the model with fixed slopes as the model with random slopes. So this is telling us the random slopes don't really seem to help us predict the data here. So the fixed slopes model performed a little bit better. And so Bayes factors are always an odds ratio. So above 1 means that they favor one model, and below 1 means they favor the other model. So here is Bayes factor for this model. So here I'm comparing the one with fixed slopes to the one that only had MStat. So here the data was 2.84 times as likely to be produced by the model with all 3 predictors as the model with only MStat. So it does seem like pain and active do help predict the data above and beyond just MStat. So we can you compare multiple models at the same time using Bayes factors. They call this the M-close case. So this is the relative probability of each proposed model against each other proposed model. And we could call this on bridge objects with the post-prob function. So the interpretation of these results here is that if we assume that one of these models is the true model, there's a 0.737 chance it's fixed slopes model, a 0.295 chance it's the MStat only model, and a 0.004 probability it's the random slopes model. So an important caveat here is that in hierarchical models, model fit is assessed using all parameters. This includes the cluster-specific parameters, so all the cluster intercepts and slopes. So it's possible that the random slopes model produces poor fit really because the cluster slopes are difficult to estimate. And they're not very stable and they don't fit the data very well. It's also possible that the random slopes model produced fixed effects that would have estimated the data better. That's not what this is testing. There are ways to test this using Bayes factors, but they're a little bit convoluted and not very easy to demonstrate quickly here. So this analysis doesn't rule out the possibility that if we really just wanted to best estimate the fixed effects, we should still be using the random slopes model. We can actually test this with a slightly different approach using cross-validation. This isn't as popular an approach right now, but it's the approach that was taught to me as being superior, and I actually agree. I think it's a great approach, but it's not as popular. It's not what you learned in lecture. So for now, I'm going to leave that as separate material. If we get to it next week, we'll get to it. If not, it'll be bonus material. We can also use Bayes factors to test specific hypotheses rather than compare models. And this is one of the things that I think frequentists feel really comfortable with, and one of the things that anti-Bayes factors people worry about, but I think it can be useful as long as you interpret the results correctly. So for this, we can use the Bayes factor parameter function from the Bayes test R package. And so here we can test either a point null hypothesis, and this is the most similar to what we're familiar with. So we can test the null hypothesis that our parameters are 0. We could test a null region, which is kind of cool. So we could say that test the hypothesis that theta is, here I'm saying that it's between -1 and 1, but really we could also test that it's not between -1 and 1. And I think that's probably more common. But you could do either one. And then you could also do a null direction. You could say that theta is less than 0, so you can test whether it's negative or positive. So here we're going to use the fixed slopes model to demonstrate the point hypothesis, the point null, since it's the most familiar. But here's a little vignette if you're interested in saying a little bit more about it. So when testing a point null, the math is actually pretty easy for the Bayes factor. So this is a little bit faster. What it's essentially doing is it's estimating the ratio of the height of the prior distribution to the height of the posterior distribution at the null point. So it's saying that was the probability that the parameter is 0 higher for the null, or higher for the in the prior than it was in the posterior. If it's higher in the posterior, then that means we have evidence that the data has provided evidence that the parameter is more likely to be 0 than it was in the prior and compared to other possibilities. However, if the posterior is lower at 0 than in the prior, it means the data has moved us away from 0, and that's provided evidence against the idea that the parameter is equal to 0. So here we demonstrate how we can do it. So I believe these are the defaults, but I just made them explicit. So I entered the model. I set null equals 0. You can make it any point, and I specified I wanted fixed effects. And so here we get our little output table, and here's how we interpret these results. So I believe the correct, most precise interpretation here is that the coefficient of pain is 0.61 times as likely to be 0 in the prior as the posterior. And this is evidence for the null. And this is not something we can do in frequency analysis. We can't provide evidence for the null. And the reason is the posterior moved towards 0. There was more mass at 0 in the posterior distribution than there was in the prior distribution. Likewise, the coefficient for active is 5.47. So it's 5.47 times as likely to be 0 in the prior as the posterior. And so this is evidence against the null. The posterior moved away from 0, just less mass at 0 in the posterior. And likewise, the coefficient for MStat is more likely to be 0 in the prior as the posterior, and this is a much stronger result. And we can also visualize this, which is kind of neat. So we can plot this Bayes factor result. So we don't actually have to load up ggplot or Papaja, I just did that to make things look nicer. So what we actually see here are the two distributions plotted over one another. And so we see that our prior is nice and flat. That's what we, that's the way we specified it compared to our posterior. And so what we see is that here for MStat, the mass at 0 is all the way up here. This is the peak of this distribution, and it's really high. Whereas in the prior, we said that there wasn't a ton of mass down here at 0. So we're saying that we've gained a lot of confidence that MStat is 0, or that it's more likely to be 0 than what we thought in our prior. And since our prior was flat, this is evidence that MStat 0. On the other hand, active, we see that the prior was higher at 0 than the posterior. The posterior is quite low at 0, so this is evidence that the data has provided evidence that active is not 0. And it's hard to see with pain because they're pretty close together, but the posterior is a little bit higher. But another thing we note with pain is look how tight this distribution is. We really this was reflected in the credible interval. We really have a lot of confidence that pain is in this very weak negative range. So this is in some ways a less interesting result and maybe one of the risks with Bayes factors. Yeah, we've gained a little bit of evidence that it's 0, but really most of the evidence that we have is that it's not 0, but that it's very slightly negative. And so slightly negative that we probably don't care if it's 0 or not. It's not that important, the distinction. So this is just going over those plot interpretations again. And then the last thing I wanted to go over is effect size. So there's a Bayesian variant of R squared. It's very similar to traditional R squared. It's defined as the mean of the following formula across all posterior draws. So each draw, you can calculate this formula for. So it's the variance of the model predicted y values. So these are essentially the y hats, divided by the variance of the y hats plus the residual. So again, this is the proportion of the model estimation divided by the total variance in the outcome variable. So it's calculated a little bit differently than frequentist R squared, but it's a very similar idea. And then again, you do this for every single iteration, every draw from the posterior that you took, and that'll give you your Bayesian R squared. And you can get a confidence interval for it too. We could use the R2 Bayes from the performance package to get it, and we can even get a conditional and a marginal R squared. The conditional is similar to R squared FBT, so this is the fixed and random effects, whereas the marginal is only the fixed effects, so R squared FT. And so here I call it, and we get our conditional and marginal R squares, as well as credible intervals. So the interpretations about 54% of the variability in P affect was explained by the fixed and random effects. About 11% of the variability was explained by fixed effects.